Okay, so let me start. So today I'm going to talk about this subject, spin current statistics for the quantum 1D XX spin chain and the Bessel kernel. So maybe this subject may not be so familiar to you because my talk is about kind of quantum spin chains, not about stochastic processes like ASIP, right? But this has some similarity to what we or you know very well, and yeah, this may be of some interest for you. So let me try to explain. Okay, so this talk is based on a collaboration with my two students, Hiroki Moriya and Mr. Nagao. This was already published in Journal of Statistical Mechanics. Okay, so if you are interested in more details, please take a look. And in fact, the contents of the talk is rather simple once you understand this quantum part. But maybe my impression is that especially for online seminars, it is not so easy to keep concentration for a long time compared to the situation in the actual room. So hopefully, maybe I can try to stop a bit earlier so that you can keep awake. Okay, so let me start. So first, I start from the setup of a study. So this is rather simple if you know quantum mechanics and especially quantum spin chains a little bit. So we consider the statistics of the integrated current of up spins at the position alpha, or maybe kind of bond between sides alpha and alpha plus 1, when the dynamics is described by the Schrödinger equation for the XX spin chain. And the initial condition is taken to be the so-called domain wall initial condition. The Hamiltonian for this one-dimensional XX spin chain is given here. And the quantity of our interest, integrated current, is maybe defined in this way, right? And the initial condition we are considering, this domain wall initial condition, is drawn here. So, for all sides to the left of the origin, initially all spins are up, and for all spins which is to the right of the origin, they are all down at the beginning, right? And then so up spins will propagate to this right region, and we count the number of up spins to the right of the position alpha. So this is the basic setting, model, and the quantity. For some of you, maybe this is just obvious. And for such people, maybe you can skip the next few slides. But maybe for other people, maybe what they may find this kind of explanation not so easy. So in the next few slides, I will try to explain really the basics about our problem. Yeah, for people who know the quantum mechanics and so on, you can just skip these parts. So maybe for many of you, time of evolution is usually given by the stochastic dynamics, especially in many cases by the Markov dynamics. But time of evolution we are considering in this talk is the quantum mechanical one, and this is in a standard way given by the Schrödinger equation, which is written in this way here. In physics literature, we usually have h bar, kind of Planck's constant, but from the point of view of more mathematical treatment, so this constant can be taken to be unity, so we simply consider this equation known as the Schrödinger equation, right? And so what are psi and h? And in quantum mechanics, in simple cases, we can consider finite dimensional state space. And in this case, H, which is appearing here, is just a Hermitian matrix called the Hamiltonian. And the psi, and this is sometimes we call this ket vector. So psi ket is an M vector in Dirac's notation. I hope most of you are rather familiar with this notation. This is just basically column vector, right? And this represents a quantum state. And quantum state means that this is not a probability, right? This is so-called probability amplitude. And to have a probability, you have to kind of square, and, yeah, which will appear just in the few lines. And for quantum mechanics, we are also interested in some averages of physical quantities and so on. And in quantum mechanics, physical quantity is represented by some Hermitian matrix, which is denoted by A here. And its average is maybe at time t is defined or given by, is denoted by this bracket, and is given by this expression. So this is a kind of row vector called bra. So bra, psi bra A and psi ket at time t. And the psi of t ket is state at time t and is described by this equality. So e to the power minus iht describes the time evolution. And so this, so psi is a kind of, is a state. And in this case, this can be thought of as a state at time t equals 0. And then with this combination, this is a state at time t. And this bra vector, kind of row vector, is given by kind of conjugate for this ket vector. So this dagger means the transpose and the complex conjugate, right? And this may be also written, this average bracket A of t can be also denoted by this, where A of t is given by this expression, right? So this is just a rewriting of this. And in physics, this is usually considered to be corresponding to two different ways of considering time evolution for quantum mechanical system, the so-called Heisenberg picture and the Schrödinger picture. So this, when we are thinking that the state evolves, then this is the Schrödinger picture, and this is equivalent to considering time evolution for the operator. So this is the so-called Heisenberg picture. Anyway, when we consider averages, so these two pictures become the same with these combinations, right? Yeah, so this is really the basics of the quantum mechanical time evolution and considering averages. So maybe at this point, one can compare these definitions with stochastic processes, the case of stochastic processes, which would be more familiar to you. So in the case of Markov process, time of evolution is of course described by Kolmogorov equation, and its forward version can be written in this way, in a formal way. So then P is a kind of vector representing the probability the system takes some configuration, and L star is the time of evolution operator, which is the usual generator, or maybe the adjoint of the generator, right? Of course, if you compare this Schrödinger equation with this Kolmogorov equation, they are almost the same. Of course, there is a difference of I factor here, but otherwise, formally, so they are the same, right? That's true, but of course, the conditions for the matrices are different. Here, H for quantum state, quantum evolution is Hermitian matrix, and L star should satisfy the stochastic condition, right? But maybe bigger difference is in taking the expectation value, considering the average. For the case of quantum state, so this is the average, but for stochastic processes, in probability theory, we take the average to be this expectation, which is defined to be this sum. And X is a kind of of course, this is a random variable, but in the case where this corresponds to some physical system, this is a kind of physical observable, and P is a probability. And we take a kind of linear sum, or take a sum of, which is linear in P, which evolves according to this time evolution equation, Kolmogorov equation. But in the case of quantum system, we consider this average, which is quadratic in psi, which is evolving according to the Schrödinger equation. So in many respects, formally, so there are some parallelism in these two cases, but on the other, there are in many cases, in fact, yeah, considering expectation. Averages makes things different, and when we try to apply some techniques which can be applied to this stochastic process, to quantum system, in many cases they don't work because of the difference of these expectations. Okay, maybe it was too long, but let's go on. So then let's define our model, the XX spin chain. First, we introduce the Pauli matrices, which are denoted by these sigma X, sigma Y, and sigma Z. These are 2x2 matrices, and slightly different matrices are also introduced, and they are denoted by SI. SX, SY, SZ are just half of these Pauli matrices. And also for these two-dimensional spaces, we introduced two bases. So one corresponds to spin up. This corresponds to 1, 0, and the down spin corresponds to 0, 1. With these notations, the Hamiltonian for the XX spin chain is given by this expression, or basically infinite dimensional matrix. And we consider the time evolution described by this Schrödinger equation with this Hamiltonian H, XX. Here, J appearing here is the coupling constant. And this represents kind of strength of the interaction between the spins at n and n plus 1. And this n means that this matrix S, nx, acts non-trivially only on the space at site n. So in tensor product notation, so this Sn, for example, this Snz is written in this way. For all sites except for n, so these are just unit matrix of size 2, but on site n, this Snz acts as Sz here, which is half of sigma z, right? Okay, so this is the Hamiltonian. Then the initial condition is easy, I think. So we consider from this special initial condition known as the domain wall initial condition, in which all spins are up to the right, to the left of the origin, all spins are down to the right of the origin at time t equals 0. Then now we come to some probabilistic object. So maybe at this point we can consider a probability the total number of transported up spins at time t at position x may be defined or written in this way. So this is so this part is state at time t starting from this domain wall initial condition, right? And so this is a kind of conjugate of this. And then, so this is a kind of projection to the state with these spins at site, Z spin at site M is given by plus up or down. And for this, so this represents a probability from quantum mechanics. This factor, each factor in this sum represents the probability that at time t, the state starting from the domain wall state and evolving according to this XX spin chain Hamiltonian is at the state specified by this SMZ. So we are thinking that we are specifying the configuration of spins, whole spin configuration, S1Z, S2Z, and so on, right? Yeah, we specify the Z component of the spins. Then among these configurations, there are some configurations in which this number, so this corresponds to the number of up spins to the right of the alpha, and there are configurations of spins in which this number is equal to m. So then this would represent the probability that the number of up spins to the right of alpha at time t is given by n, right? So this is the interpretation of this expression. Sorry, yes?
So can I ask a question? So the SZ, these are the spin matrices, right? These diagonal. So how can the sum of them be equal to a scalar?
Sorry. So there's a confusion here. You're right. Sorry, yeah. sorry. So here, of course, these Sn, X, Y, Z are matrices, right? Infinite dimensional matrices. But sorry, so in this expression, these are just numbers taking values plus or minus 1. Sorry. Sometimes it is useful to kind of make a confusion on purpose, but yeah, here it was not a good idea. Sorry.
I see. So the SCs are they're either 1 or minus 1, or I guess they're
down. Yeah, sorry, up or down. Yeah,
up or down. So the basis is
yeah, exactly. Yeah.
Okay. Okay. And so these are then vectors indexed by these up or down. Okay.
Right. Okay. Okay. So up to this point is just a formulation of the problem and so on. So there was already one question, but are there other questions so far?
Well, there was the question, I think it's similar. What does capital N equals little n in the sum mean? I guess, again, it's just about understanding what this.
But maybe that's related to your question, right? If this is regarded as just sorry, in this case, not plus 1, 1, 1, plus minus 1/2, because we are considering scalars corresponding to this one. Yeah, because we are considering so-called spin Z axis basis, even though this is a matrix, when we specify this axis, then this becomes kind of scalars, right? Numbers. That's why we make kind of confusion here. Anyway, so once we understood this as a plus minus some scalar variables taking values plus 1/2 or minus 1/2, then I think the meaning is clear. Further questions so far? Okay, so then let's go on. So of course, we are interested in this statistics of this quantity n of t. And to study such statistics, maybe it is useful to consider moment generating function as usual, which is denoted by chi of lambda t here. And this is denoted by bracket of e to the power lambda n of t. So maybe as in the case of usual probability theory, this can be defined to be a sum like this. So small n, so this is the number of upspins to the right of alpha, takes values only from 0 to infinity. So this is a kind of complete sum. And there is a probability that this capital N of t is equal to n. And then we just multiply this by e to the power lambda small n and take a sum, right? So this is a probabilistic definition of this moment generating function. But at this point, maybe you may wonder, so we have been already introducing this bracket notation for some quantum mechanical average and whether this is consistent. And in fact, this is consistent. And so n of t was also defined, sorry, was n of t, yeah, in this case, SNZ is matrix, and so this n of t is also matrix. And then quantum mechanical average is defined in this way. So then this notation makes sense from such point of view. And this is, according to the definition, this can be written in this way. And in fact, one can do a little calculation to see that this notation is consistent with this definition. So in that sense, we don't have to care too much about the difference. But anyway, we are interested in this quantity. Okay, so this is one kind of interpretation of this capital N of t as an integrated current. This is just a small remark. So maybe we can consider time evolution for this S alpha of z at time t by using the so-called Heisenberg picture. So then, so this time derivative is given by this commutation relation of Hamiltonian and this variable S alpha z. And this one, after a little bit of calculation, one sees that this can be written in this way, where J alpha is taken to be this expression. So because this is a kind of discrete continuity equation, J alpha can be considered as an instantaneous current, even though this is an operator or infinite dimensional matrix. But anyway, n of t, which was written in this way, can be also written in this way by just taking, by considering integral over t. So then one sees that, so this n of t can be also interpreted as integrated current in this sense. So this is just a small remark. Okay, now comes our main theorem, which is rather very simple. So we are interested in this moment generating function of this n of t, which was defined in the previous slide. Our main statement is that this has a very simple expression in the form of Fredholm determinant in this way. 1 plus e to the power lambda minus 1 and k Bessel with parameter alpha, where this kernel is given by the usual Bessel kernel with parameter alpha. And as most of you probably know, so this Bessel kernel is a well-known kernel which describes statistics of eigenvalues at the spectrum edge, especially the hard edge case. And as you can probably imagine, once we have this type of formula, by using some asymptotic methods, one can study large T behavior of this probability distribution from n of t. And this is what we are going to do in the next, in the following. Yes. So now in this next section, we discuss about asymptotics. Sorry, this is a very simple introductory slide. So we are interested in large deviation, in particular for this integrated current n of t for XX spin chain from domain wall initial state. But I think most of you know, but just in case, if there are some people who are not so familiar with large deviation, so this is, this is, as the name suggests, we are interested in deviation which are pretty large. To consider large deviation, it is most useful to consider the very simple case of Bernoulli random walk. So let psi I to be IID Bernoulli random variables, which takes values either +1 or -1. So these are independent. And so they take values with + or -1 with a probability 1/2. And we consider random variable xn, which is just a sum of psi1 blah 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 to psi n. Average and variance are computed explicitly and easily. And the average is, sorry, so this is, sorry, this is n/2. Sorry, yeah. No, in this case, this is zero, sorry. Yeah, sorry. And then the variance is n/4. So then from this one can consider, we can think that the typical fluctuation of the distribution for this random variable is scales like square root of n, right? And as you know, as all of you know, so this distribution becomes Gaussian in the large n limit. But we could be interested in the fluctuation at the scale of n. So we consider the probability that this xn is behaves like is ny. So this is a not completely precise statement, but basically it means that this probability tends to 0 as exponential function e to the power some function times n, and this some function psi, which depends on y, is called a rate function. And in this particular case of Bernoulli random walker, so this function can be calculated rather easily and is given by this binary entropy function, which looks like this. Right, and yeah, as I mentioned already, we are interested in similar large deviation function in the case of XX spin chain integrated current. Right, so there have been several results before our work. In particular, of course, before going to large deviation, we are first interested in average and variance and so on. And for exactly the same setup, XX spin chain, starting from domain wall initial condition and about integrated current, average was calculated by these people, and they understood that this behaves like T over pi when T is large, right? And variance was also calculated by these people. Here is a pole here, and so this was calculated to behave like log T for large T. and with some constant c.
Tomohiro, presumably in your definition of NT, you're looking at everything pat to the right of 0, not like before it was alpha, but.
Sorry, yeah, sorry, thank you. Yes, yeah, from some time on, yeah, we just focus on the case of alpha equals 0, and yeah, sorry, so these statements are for alpha equals 0 case, sorry, thank you. And this constant c in their work was written as a sum of a few definite integrals, and they calculated this constant c numerically to be this number. Okay, and our result about the large deviation was that, yeah, sorry, here I'm writing that we are considering alpha equals 0 case, and the large deviation function behaves, the probability that this integrated current is given by AJT. So this case like T and the coefficient A. J is a coupling constant, but maybe one can think of this just unity. So basically this is the situation we are considering the situation in which integrated current is AT, right? T is the time and A is some coefficient we are fixing. And for this probability, of course, this decays rapidly as T becomes large, and the behavior is given by e to the power minus t squared, and the rate function is denoted by psi of A, and we have some formula for this rate function psi of A. And to describe the result, let's introduce the complete elliptic integrals of the first and second kind, which are given here. And by using these two functions, our rate function is given by this formula, kind of parametric representation. Let's take f of r to be this function, and maybe let's take a of r to be this function in terms of e and elliptic integrals. And the form of the functions depends on r, which is the variable here. And we also introduce another function f of r in terms of this a of r here and k and e, elliptic integrals. So then with these two functions, one can define this function psi of A, right? And then, R of A here is the inverse function of A of R. Right, and if you plot by using mathematical or something, A of R looks like this and F of R looks like this. Yeah, so this is basically the result for the large deviation, but I have to say that these results have, so for the moment, this result has been obtained by using some calculations which still involve some change of limits, which we haven't completely made rigorous, right? So at this point, we have to check more carefully at this point. Anyway, but once we have such a formula, for example, we can compare with the numerical simulation. And in fact, maybe for some of you, so maybe you have done some Monte Carlo simulation for stochastic systems like A7 and so on. But now we are considering quantum system, so we cannot use the usual Monte Carlo simulation, but there's a very nice numerical algorithm known as the density matrix renormalization group, DMRG. And now there's this kind of standard package which allows us to do this kind of numerical time evolution for spin chains. And by doing this for XX spin chain, and if we compute this large deviation function, then we see a very good agreement between our formula and the numerical evaluation of the time evolution. So this, you see, so the agreement is pretty well. Already at time t equal 8. So of course the large deviation should work well for large t, but from this numerical simulation, already at time t, we see a very good agreement between our prediction, our formula, and the numerical evaluation. Okay, I have already explained the main results. So in the remaining of the talk, I try to explain how we have arrived at the formulas, right? So first,
Tomohiro, there was a question. Li Chang asked, is there a way to tease out the scale of the variance of n of t from the rate function around its minimum? So do you know anything about the fluctuations? Can you guess something about it? how does the thing disappear around 0? Is it quadratic?
So around where? Here or here and so on?
Around 0. So can
Oh,
you
there.
can you infer something about the kind of central limit theorem for n of t?
Central limit theorem may appear here, right? I will come to this point later.
Okay.
Okay. Okay, so we are considering spin chain, XX spin chain, but it is a kind of well-known fact that by using the so-called Jordan-Wigner transformation, this XX spin chain can be mapped to a free fermion, which may be also somewhat familiar to you. And so this Jordan-Wigner transformation is written here. So this is so these SKs are spin matrices, right? And plus minus may have appeared for the first time in the slide, but this is just a sum of plus 1 and minus 1 with coefficient I here. And if we compose these particular combinations of S plus, Sj plus, and so on, and if we define them to be Cj dagger and Cj, one can check by using commutation relations of Sx, Y, Z, that these objects Cj dagger satisfy the canonical anti-commutation relation given here. And this means that so these objects Cj and Cj dagger are fermions. And what about the Hamiltonian? So spin chain Hamiltonian, XX spin chain Hamiltonian, which was written in terms of spin variables, can be also rewritten in these fermions, and this is it looks like this in terms of Cj dagger. And in fact, this Hamiltonian is quadratic in Cm and Cm dagger. So this means that so this is a so-called free fermion model. Free fermion model also appears in KPZ stuff too. So maybe some people are familiar, but also for XX spin chain. So this is very much related to free fermions. Also, the initial state, domain wall state, can be also described in terms of the spin operator. And the integrated current can be also described in terms of this fermion operator in this way. So our problem and the quantities, everything can be restated in the language of fermions. But so this part is kind of standard once we understand this mapping. So then I will omit some procedures. But anyways, by using kind of standard techniques of free fermions, one can show that our generating function can be written as determinant already. So this was the result already several years back by Iceland Lux. So they found one formula, determinant formula for the generating function, moment generating function in this form. So this is very much similar to our main result, right? But in this case, they found that this quantity can be written in terms of discrete Bessel kernel, which is written in this way. Of course, in KPZ community, this is also a familiar object. So this appears in the study of PNG model. But yes, so that same kernel also appears in this XX spin chain. That's fine. So at the beginning, we thought that by just studying this expression in terms of discrete Bessel kernel, maybe one can study the large deviation, but it was not so easy, at least for us. So then we spent some time to try to have a different expression for which it would be easier to do asymptotics. Then we arrived at the formula I showed you, right? But maybe for people here, maybe one can just do large D asymptotics by using this expression in terms of discrete Bessel kernel. That would be also interesting one kind of little project one can try to do, I think. Okay.
Tomohiro, may I ask a question?
Yes.
So you have the discrete and continuous Bessel kernels, but do you ever see point processes governed by this kernel? Do you just get these determinants, or you can see correlation functions and some other expressions with the same kernel that would be meaningful for the quantum spin chain?
Right. I have to say, we haven't really thought about it carefully. So for the moment, we are just happy to see this equivalence of the determinant. But maybe it will be useful to consider such a...
It's just that this formula is a formula for the average of a multiplicative functional on the determinantal process with this correlation kernel. So, you know, maybe there is more than one formula, that's all.
Right. No, yeah, that's certainly true. Yes. Okay. But yeah, let me go on. Yeah, so this is a kind of a main observation in this talk, right? So in fact, at some point, we noticed that there's a very, very simple identity between the Freedom determinant for the discrete Bessel kernel and that Freedom determinant for the kind of continuous Bessel kernel. So this is just identity. So this kind of object has been known already for a long time in PNG and so on. And this determinant, Freedom determinant, was also very well known from the work by Tracy Wiedemann and so on. But it seems that nobody has really written down this equality until our work, right? So this was our observation. Yeah, so I was a bit curious and almost worried. Maybe somebody had already found this formula. So I asked Peter Forrester if he knew this formula before, but his answer was that at that point, yeah, he didn't know it so explicitly. But once he saw the formula, then he could look at his book, of course, and found that by combining this formula, one can find this identity, right? Anyway, yes, this is probably this has, yeah, maybe, yeah, of course there are many specialists here. So if somebody know that this identity was written explicitly before our work, please let me know. Yeah, yes. Yeah, but after all, our proof was very, very simple. So we just expand this determinant in terms of traces and compare the coefficients. Right. Yeah, that's it. And then so once we understand this and combining the result by Iceland Lux and this observation, we arrive at our main theorem. So, sorry, this is, yeah, this is a very, very simple thing, but still, I think, you know, the model is simple and the result is simple. In that sense, I think this may be of some interest for you. Okay, so once we have this formula, we can consider some limiting cases and so on. One particular case is when lambda goes to minus infinity. And in this case, by definition, this generative function goes to the probability that current is 0. And this means that the quantum state starting from domain world initial condition should return to the same domain world state. So this is also called the return probability. And this had been studied by other people a few years back. And this was calculated with e to the power minus t squared over 4. And this agrees with the special case of our formula, of course. And for large...
Tomohiro, sorry, I just a quick comment. I'm a bit slow, too early in the morning. About the previous slide, so you asked Peter Forrester. So Peter and I had a paper about 20 years back where there were correspondences between distributions of the longest increasing subsequence and the hard edge gap probability, or the hard edge distribution of the leftmost eigenvalue. So those are probably z equal 1 special cases of the identity that you're looking at.
Maybe that's correct, yeah.
So those can be proved by just looking at topless determinant representations for both gap probabilities. You just look at the two topless determinants and they're just the same. It's just you can interpret them in different ways. And I don't know which formulas Peter was showing you in the book, but this sort of points to me to the previous question I was trying to ask, that there is more than just one formula somehow. There has to be a whole structure that sits behind it that somehow works in the background. But I have nothing more to say. Just wanted to point out.
Yeah, thank you. Yeah, well, I think, yeah, probably there's, some nice structure which is for, how to say, so this is just a special case of such thing. But yeah, until now, I haven't found enough time to work on that. But if you are interested, yeah, of course, yeah, just most welcome. Okay, so yeah, another limiting case in which N and T are large with this condition. So this was studied by Tracy and Widom, the original paper about this Bessel kernel. And by using some formulas in the paper, it is suggested that the first derivative of this, our rate function, at the left edge, a equals 0, should be given by -2, and this can be confirmed from our formula. Okay, and then so the rest is really just a kind of standard thing to study large deviation, basically. Yeah, so we now have a continuous Bessel kernel expression for our generative function. We want to study the large deviation. I think there's a kind of more direct way to study this large deviation directly for continuous Bessel kernel. But yeah, I thought that maybe it is easier to use some known results for finite n Whishart matrix, because as probably all of you know, that the Bessel kernel appears as a large n limit of Whishart matrix, and for Whishart matrix, there have been several works on large deviations. I thought that maybe one can use that. And this is how we proceeded. So this is a well-known statement. When X is an n by n Gaussian matrix with Gaussian distribution, when we consider this particular combination, then this is the Whishart matrix. And then, as is well known, the joint eigenvalue probability density for this Whishart matrix is given in this form. So this is very similar to the GUE case, but now we have exponential weight, and this is, yeah, eigenvalue density for Whishart case, where alpha is n minus n. And then by taking log, so this becomes e to the power sum of log, xj minus xk. So this is related to some point particles with Coulomb interaction in physics terminology. So this is sometimes called Coulomb gas. Right? And the Bessel kernel appears from special large n limit of this Whishart kernel. The Whishart kernel can be written in terms of Laguerre function in this way. And if we take this particular scaling limit for this Whishart kernel, then we get a continuous Bessel kernel with parameter alpha, right, at the hard edge. And in the limit, we wanted to consider the number of particles, right? So for this case, in the language of Bessel kernel, we want to consider the interval 0t squared. And for large but finite n, we should consider this interval. Right? And in the large n limit, this interval for large n Whishart matrix corresponds to the XX current. Okay, and so about the large deviation for the Whishart matrix, as I mentioned, there have been several works by Majunda and so on. Of course, more rigorous versions will be possible by methods by Johansson, Gione, and many others. And recently, there have been many activities on KPZ large deviation, right? So they are all related, I think. But this large deviation of Whishart matrix is rather basic one in a sense. But anyway, so they, or by using rather standard methods now, we can study the large deviation for this Whishart matrix for large n. And when we consider the probability that the number of eigenvalues in a given interval I is given by kappa times capital N, this behaves like e to the power minus n squared some function. So this is the rate function. And this can be this rate function can be calculated by so-called Coulomb gas method. And to do so, we introduce most probable density with a condition on number of eigenvalues coming from this condition. And of course, this should satisfy the normalization constant. And this satisfies this condition that the number of eigenvalues in the interval is given by number is n, small n, and the ratio is kappa. And we also introduce this resolvent by using this this density. And then the rate function is given by, in terms of these variables and so on, given by this expression, where mu and eta appearing here are also described by this resolvent G and the lambda plus minus, which are the edges of the support of this rho star. And lambda minus are compared with this expression t squared over n squared. So it is kind of natural to introduce parameter r here. So this r is the r, which appeared in the description of our formula, right? But anyway, and we are interested in this particular interval. And for this particular interval, if we try to compute this probability that the number of eigenvalues is given by some cap, something like cap n, then we can calculate the large deviation rate function in this way. So this is a little bit tricky calculation because we are taking large n limit, but we also want to take t to be large. But if you look at the formulas, we stand that when we consider the large deviation for large n, we put n capital n squared here, right? And we want to kind of replace it by t squared. And by doing the calculation, it is rather obvious to see that because this combination appears in a natural way, so this large deviation function for large n would be replaced by rate function for large t. But anyway, in this way we proceeded, and then we see that for the rate function, these two elliptic integrals appear in this way. Yeah, so this is kind of basically the how we arrived at the formula, derivation of our formula. And once we have the formula, we can consider a few things. For example, the Gaussian fluctuation around the most probable point. So this is not completely obvious, not too trivial, because at the minimal point, the most probable point, this is not analytic, but we can consider maybe small r variation from the most probable point, and then we can do this kind of calculation. And by combining them, we see that small rate function at the most probable point plus minus delta A behaves like delta number of eigenvalues squared times this function. And of course, this delta, so of course we are putting this as an exponent, we are considering e to the power minus t squared rate function, right? And then this corresponds to the Gaussian behavior around the most probable point with the variance given by log t. So this is consistent with the previous result by Paul and others, that for large t, the variance behaves like log t, as I mentioned almost at the beginning. And so this is a rather simple expansion calculation, but now we have a Bessel kernel expression. So by doing some asymptotic analysis of this Bessel kernel, one can do a little more calculation to show that variance for n of t is given by this expression. Sorry, maybe there's a lower order term, but up to constant, this is the formula. So this is the main term, right? Appearing here, log t with this coefficient, but the remaining constant term is calculated in a very simple terms, and they are just given by log 4 plus gamma plus 1, and the gamma is Euler's constant, right? So in fact, this is the constant c, which I mentioned when I explained the previous work by Paul and so on. And in fact, so this formula means that the constant c. So maybe I show you once again to recall. Yeah, so I mentioned that so Paul and collaborators calculated C in this way, right? At this point, I think there were not so simple formula, but by doing our analysis, we noticed that this constant is simply given by this formula. Right? Okay, so this is all I wanted to say. Sorry, after it took almost 1 hour. Anyways, let me summarize. So we studied the integrated spin current for very simple model known as XX spin chain. For the moment, we just start from the domain wall initial condition. This is like step initial condition for ASEP, right? And our main result is rather simple, explicit determinant formula for the generative function in terms of the continuous Bessel kernel. And because of this formula, we can do some asymptotic analysis, and we found some large deviation rate function, which match at least very well with the numerical simulations. But a complete proof has not been given, so this is one little open question. Okay, yeah. One interesting point, yeah, maybe for Alexei it was also surprising, but for us, it was interesting to see that there's a nice connection between discrete Bessel kernel and the continuous Bessel kernel. And as you can imagine, so our setup is very simple. So, but formulas are also simple, but there should be various generalizations. So that would be interesting to pursue, I think. More from a physical point of view, of course, X spin chain can be kind of realized in actual material, like compounds given by these, or recently by using cold atoms, they say that they can make something like X spin chain. So there's a possibility that they can observe a rate function in the real experiments, hopefully. From a technical point of view, of course, as I mentioned, recently there's very strong activities on KP's large deviations. And of course, they look pretty related, right? So that would be interesting to see how, if or how much they are connected. And also, so usually in our community, I think we have been mostly working on the case where conservation law there's only one conservation law. Sometimes we may consider 2 or 3 conserved quantities, but it is not so typical, at least until now, I think, to consider the case of many or infinite conserved quantities. But XX spin chain is such an example. So this is quantum spin chain, which has infinite number of conserved quantities. And there are, of course, many other models and so on. And of course, the question itself is also relevant for such more complicated cases, and it will be very interesting to study such problems for these other systems and so on. Okay, yeah, so sorry, I was hoping to finish earlier, but it's really 1 hour talk. But anyway, thank you for your attention.
Thank you very much, Tomohiro.
Thank you. Mm-hmm.
So we have time for questions. If anyone would like, just please unmute yourself and shout out a question.
I have a question.
Yeah.
Tomohiro, have you? It seems that the quantum. Dan, by the way, I don't know if you can see faces. I guess I can also. Should I also unmute my face?
Maybe I want to see your face to talk, no? No? There are too many participants, so it's difficult to...
So I can see my face, but of course it's on my screen. Maybe it appears if I talk.
Right.
Tomohiro, if you unshare your screen, that's one way. Okay. Otherwise, you can push, there's like a button with like a 3x3 square. Okay, and now you'll see everyone.
So I have a question. The process that you're describing seems to be very familiar to me because it seems to be a process of Borodin-Olshansky in disguise called the Plancherel process. And so there is a question at the end. Jeremy and I wrote this quantum mechanical formalism that you have, I believe, I conjecture, in the finite temperature setting. So with this, you know, in the free fermionic setting, but in the finite temperature. And if you take the temperature to 0, it seems that what you end up with is exactly the Hamiltonian and the process you're describing. Now, this is, of course, before the pre-limit, before the large deviations computations and whatnot. So in that sense, I suspect that there is actually a full determinantal structure behind everything. And furthermore, I think you can actually do more. So for example, you can probably consider, by the way, the Plancherel process is related. If you look at my finger, there's a Plancherel measure here on the wall. I don't know if you can see it. Anyways, I believe that, for example, you can probably consider the finite temperature setting as well, or other types of boundary conditions. So finite temperature would be on the right and on the left, you have essentially arbitrary Maya diagrams weighted by their energy. So by Maya diagram, I mean a sequence that's infinitely to the left, it's up spins, infinitely to the right, it's down spins. And but in any case, I think just the formalism is. So if you want, I can give you a link to the exact formula of the finite temperature formalism that we wrote down, and then it will take you half an hour to figure out whether it's the same or not, because taking the temperature to 0 is very easy.
Right.
But I suspect that this is indeed the Borodino-Olshansky, at least the way you described it, this is the Borodino-Olshansky Plancherel process, where your time plays the role of, I guess, the Plancherel parameter in that setting.
Okay. But I haven't maybe understood that. Do you think that that's they are related to some quantum spin chain or something?
No. So what we did was we just started from the free fermions. So you did something extra because you started from the spin chain and then you did the Jordan-Wigner transformation, right? Right. But after you do the Jordan-Wigner transformation, your transfer matrix seems identical to the 0 temperature Borodino-Olshansky so-called transfer matrix. Yeah. So after Jordan-Wigner, things, at least at the finite level, finite everything, things seem to be the same.
Determinant process is really standard ones, right? So very standard things appear in our analysis after all. But I would be kind of more interested in kind of physical systems, right?
But yeah, so that's why I suggested maybe you or we, or I don't know, can look at, for example, finite temperature. So you do the same thing, but then maybe there is a natural notion of XX in finite temperature. So for free fermions, there is. It's just the quantum mechanical finite temperature. Right. You know, you have to do T to the energy and then something to the chemical potential, the usual stuff.
Okay.
And then take the trace over all Fock space, in that case, overall spin configurations that are allowable and everything.
Yeah, okay, yeah.
But in any case, I think it's more than just a coincidence that that the Bessel kernel appears, and I wanted to suggest this.
Right, okay, thank you.
Very nice. Other comments, questions?
I have a question. If I understand correctly, the XY chain is also free fermionic.
That's right.
So
that should be possible.
Do you think it's going to be very similar? Because now there's a connection with the random matrix object. It's curious whether it's going to connect to the same random matrix objects or different ones.
So again, we haven't thought carefully, but I expect that it's pretty similar. But yeah, we have to see. One has to see, I think.
Yeah. And it's not a question, it's a comment. I went down to the references to see where the discrete Bessel kernel shows up first. And so it came down to a paper by Schutz and Untitled and Drakos back in '98, where they were.
Yeah, that's basically the one which I showed you, I think, in the slides. So
no,
basically the average. No?
I think you showed Eisler and Drash, which is a later paper based on that.
Before that, yeah, I showed
Yeah.
some two papers who calculated the average and variance. And the first one.
Right. Okay, maybe I missed it, sorry. But the curious thing to me is that there are expressions sort of involving the discrete Bessel kernel a year before that kernel appeared in the longest increasing subsequence.
That's
of course,
right.
they don't state it as a kernel, but the expressions are there.
Yeah, that I kind of noticed. Yeah, also, yeah, almost at the same time, completely different context, similar.
Right.
Subject.
Well, whether it's completely different or not, I don't know. There is a domain wall, step initial condition in both cases, right? So something is happening. There's a, or maybe what Dan is saying is some more explicit bridge. I don't know.
Yeah.
I sort of have a, I don't know, question. Like you take trivial SEP, the same domain wall boundary condition, and everything is somehow, all the cumulants are the same. Average is root of t, variance is root of t, third cumulant would be root of t, and large deviation would be e to the minus root of t times something, times this your function psi of a or something like that. And here they are sort of different, so average is t, large deviation you have t squared, variance is log of t, so somehow, I just for myself wanted almost like blah 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 explanation. So log of t, I would think that is incompressible, this free fermions, whichever. But for instance, did you you probably computed, but for instance, how, I don't know, third cumulant looks, how it depends on time.
For which case? For this XX?
For your case, yeah.
For third cumulant.
Yeah. You computed second cumulant's variance. It's log of t. First is t.
I think that I did. Sorry, but I have to admit that a student did it, but I cannot remember now. Sorry. I think.
Okay, maybe one more question, and it's just shooting in the sky. But the very same. You take SEP or TASEP, whichever you prefer, with the domain wall initial condition. And okay, definitely from that point of view, one-dimensional system, what you consider, current is the most natural thing. But from the other case, we all know that if we take SEP or TASEP, we also can think about it as a corner problem, and so it's kind of growing interface in the corner problem. And this current would be just, along diagonal, one direction. It would be, position of that along diagonal. But we can also compute, at least in a sense, if you, okay, it's natural quantity, of course, but, we can, for instance, also compute, I don't know, the area, how much area, melted, so to speak. We started, and so it's just a different observable. And somehow I kept asking people in the field, I don't think anybody really studied, in detail, any large deviation of that quantity of area. We computed a few moments of it, but, but just, not large deviation, not full large deviation. But somehow question is any sort of similar mapping for quantum system,
I think so.
Would be somehow some corner analog of in quantum case.
I think so. I explained using kind of continuous time dynamics or spin chain, but of course it's a continuous time limit of the vertex model, right? And in the language of vertex model, one can draw two-dimensional pictures, and one can see some propagation of upspins in two-dimensional space. So this is pretty similar to corner growth.
I see. So, and the limit shape is known,
Limit shape is
okay. If I forgot about fluctuations, just focus on the shape.
Yeah, I think yes. So that's more or less related to kind of computing free energy. I think, and that's possible. I think.
I see.
But the fluctuations has not been really studied, and this is just one one of the first examples, I think, to study fluctuations for quantum system.
Tomohiro, just picking up on a little bit of what Pavel was asking. So you compute the limit of n of t over t. You can compute that limit of the sort of law of large numbers. And that was with setting alpha equals 0. Of course, you could consider alpha varying with t as well and get some sort of profile. And then you had said that you expect that this solves, well, that this is related to generalized hydrodynamics. So can you kind of formulate what is the system of PDEs, or what are the kind of infinite dimensional version of hydrodynamics that you should be solving here? Or is there some simpler equation? It's not going to be Burgers and the usual.
From the point of view of generalized hydrodynamics, our case is rather special. In one sense, this is after free fermion case, X is correspond to X spin chain. So in this case, GHD equation becomes very simple, right? Almost trivial. But another thing is that so we are considering so-called zero temperature limit dynamics. But basically, the GHD type argument are expected to work for finite temperature case, and the zero temperature case is a bit special. So I think there are some works in that direction, it seems, but because in quantum mechanics at zero temperature, somehow the correlation becomes stronger. So kind of naive application of GHD may not be justified, I think. And especially the appearance of this log T variance. This does not seem to be it does not seem to be possible to such behavior from GHD argument, it seems. I don't know completely. That's what I understood from some discussions with others.
The other question is,
in general, I think it's an interesting question. So I'm very curious about more other systems and so on by using microscopic calculations and compare with predictions from more hydrodynamic approaches and so on.
So when you look at time evolution of free fermions, you end up with these extended determinantal point processes. So do you think, or have you thought about whether you could access multi-time behavior for your system in this manner, or is it somehow a different notion of time?
I didn't really think about it carefully. But so how to say? So there are a few steps of mappings, right? First from XX to fermions, and there's a mapping from. So in the language of free fermions, the discrete Bessel kernels is more kind of natural. It naturally appears, but to do asymptotics, at least for us, it was kind of necessary to go to the continuous one. And in this mapping, there's a non-trivial way of change of looking at things, right? For example, at this point, I'm not sure how the two-time situation in the original setting can be really mapped to nice objects in the mapped system, right? But maybe one should consider more carefully.
Tomohiro, can I ask another question?
Yes.
To get this Fredholm determinant, do you end up using Week's lemma at the very end?
Week's lemma.
Some sort of weak lemma, or
yeah. Well, but this was already kind of contained in previous work by Eisler.
Right. Yeah. Because then I imagine that multi-times can be obtained just by splitting the time you have into smaller times and inserting the projectors that go into Week's lemma in between at different times. I don't know. I mean, formally, whatever that means, but I'm guessing that it might be feasible.
Yeah, of course. In some formulas, there's a standard way to consider multi-time, right? But
that's what I have in mind.
That could be very mapped to the original situation, right? But one should think, yeah.
Any other comments?
Yeah, I've got a question, perhaps a little naive. I'm coming at these problems from a mainly classical perspective. So what I'm interested in are the sort of parallels in the quantum setting between Glauber and Kawasaki dynamics. So the non-conservative for the conservative dynamics. So what are the quantum analogs here? I'm presuming this is a quantum analog of a non-conservative dynamics. It's spin flip rather than spin exchange. Is that correct? Is it a Kawasaki version of this quantum system?
Yeah, of course, the number of spins are conserved. In that sense, it's similar, yes.
Yeah, because if you have a hydrodynamic picture in mind, the Kawasaki is very natural because that preserves the spin fractions.
I think this is Kawasaki, is what Tomohiro
This
said.
is Kawasaki.
It involves nearest neighbor spin.
Ah, okay. It's exchange, it's not spin flip. Thank you.
Yes, spin exchange.
Okay, thanks.
Okay.
Okay. Any other comments? This was a very nice discussion section. Okay, so if not, let's, everyone who's still around, let's all thank Tomohiro for a very, very nice talk, and good night.
Thank you, Tomohiro.
Good night. Thank you. It's a bit sad that we cannot go to lunch or dinner together right after this.
Yeah, we have a midnight snack.
Yeah. Hopefully, yeah, after some time, we will see. we can really see and have lunch, dinner together. Yeah.
Yeah, well, we owe you one. We owe you a nice lunch or dinner.
Yeah. Okay, so thank you. Bye. Good night.
Bye.
Oh, Jeremy, if you're still on, we can test out your slides if you want. Otherwise, we can try.
Oh yeah, sure. But we have to use the other.
It doesn't matter. It'll work isomorphically. So.
Oh really?
Well, it's just you'll click on the other link and then do the same thing.
Yeah, actually, the main thing was just to make sure the sound was okay, because
Okay, so I can tell you the sound is okay.
It's fine?
Yeah, I can hear you.
Okay.
And you know how to share the
Alexei's
screen.
nodding his head. The sound's not okay?
No, the sound is good. Nodding is good. This would have been bad. Right?
Okay, it looked the other way. Okay, thanks. That's good enough, Jack.
Okay.